Good evening, everyone. Can you all hear me? Excellent. So I'd like to welcome you to the Royal Society and to tonight's 2018 Rosalind Franklin Lecture. My name is Professor Frances Ashcroft, and I'm the chair of the Rosalind Franklin Award Committee, and it's my very great honour and great pleasure to be able to introduce tonight's award winner, Professor Tamsin Mather. Or Mather? Do you know, I don't know how to pronounce your name. I'm sorry about that. Before she begins her lecture, I'm going to say a very few words about the award and about her, and after the lecture, I'm going to present her with the award, and which consists of the medal and a scroll. So the Rosalind Franklin Award is highly prestigious, and it's named in honour of Rosalind Franklin, who made a critical contribution to our understanding of the molecular structure of DNA, as I'm sure you all know. She was a brilliant X-ray crystallographer who took the famous photograph that led Watson and Crick to the discovery that DNA forms a double helix. The Rosalind Franklin Award is given to an individual who's made an outstanding contribution to any area of science, technology, engineering, or mathematics. And it consists of a silver gilt medal, which you'll probably see later, and an award of £30,000. The prize winner is expected to use part of that money on their own research and part of it on implementing a project to raise the profile of women in science at their host institution and in their area of expertise. So Tamsin was awarded the 2018 Rosalind Franklin Award for her achievements in the field of volcanology, volcanoes, and her ability to communicate with the public and her imaginative proposal. I don't know if you know, but there's a famous test in which children are asked to draw a scientist. In 1983, less than 1% of kids drew a woman as a scientist. It's still less than 30%, and horrifyingly, that number decreases as children grow older. And this matters because it influences adolescents' perception, not only of who is a scientist, but who can be a scientist. So Tamsin proposes to help dispel this gender stereotyping by making a series of films about young women scientists who are doing exciting and innovative science. And these are going to be posted on the web and on Facebook and accompanied by a set of teaching resources for schools. And the aim is to inspire more girls to consider a career in science and provide new role models for early career scientists, women scientists. And after all, if you think about it, what could possibly be more exciting than being the first person on the planet to discover something new? And how amazing to have a job like Tamsin's, which involves traveling to far-flung countries to look at active volcanoes. As you'll see, she's got some truly hair-raising stories, and in my opinion, it's not a job for the faint-hearted. So Professor Mather is an outstanding scientist, and she's one of the country's leading volcanologists. She did an undergraduate degree in chemistry, a master's in the history and philosophy of science, and a PhD on volcanoes at the University of Cambridge. And then she was awarded a Royal Society Dorothy Hodgkin Research Fellowship straight out of her PhD, and she moved this to Oxford in 2006 to combine it with a position as a university lecturer. And she's now Professor of Earth Scientists and a Fellow of University College at Oxford, and she continues to work on active volcanoes, and that's what we're going to hear about tonight. And in addition to her research, she actively shares her passion for science with wider audiences. She's participated in Soapbox Science, The Infinite Monkey Cage, New Scientist Live, and if you've not heard her interview on The Life Scientific, you've got a treat in store, and you can find it on iPlayer, BBC Radio 4. She's also won many awards for her work, including the UNESCO L'Oréal UK and Ireland Women in Science Award, the Philip Leverhulme Prize, the UK Mineralogical Society Distinguished Lectureship, and this year the Comet Group, of which she is Deputy Director, received the Royal Astronomical Society's Group Achievement Award in Geophysics. And tonight, she also gets the Rosalind Franklin Award of the Royal Society. So, ladies and gentlemen, I'm very pleased to present Professor Tamsin Mather, who will lecture on volcanoes from fuming vents to extinction events. As you can see, she's a poet too. Tamsin. Go for it now.
Thank you very much. And I must thank very much Cara Robinson for nominating me for this award, and Clive Oppenheimer and Lindy Elkins-Tanton for writing letters of support very, very rapidly in order to get it in before the deadline, which I really, really appreciated. I am massively honoured to receive this award, especially when I look down the list of previous recipients. Actually, Carol was the second ever award winner, so it's wonderful to have been nominated by her in particular, and a great example of mentorship. So I'm going to talk to you today about volcanoes. Volcanoes are a passion of mine, both scientifically, but they're also absolutely stunning natural phenomena. This is a picture I very much like of a volcanic eruption here. This is the Eyjafjallajökull eruption. Apologies to any Icelandic speakers in the audience. In the trade, we just call it Eyja to make life a bit easier. No one told the newsreaders this, so we had a lot of fun with people trying to pronounce it when the crisis was going on. So I would wager that there are more than a handful of you in this room whose travel plans got disrupted when this volcano in Iceland cast an enormous ash cloud over northern Europe and closed much of our airspace. So volcanoes to me have many different characters, and that kind of illustrates the first character, if you like, with them as natural hazards. So although fortunately there were no casualties of that particular eruption, it was obviously an enormous economic loss and an enormous inconvenience to many people whose lives were affected. It actually inconvenienced me in a very, very different way. I was on maternity leave with my son Dominic when the eruption occurred. So my life was turned upside down by the university press office, who kept ringing me up, trying to get me on various television and radio channels to comment on the eruption. I actually very nearly ended up going on Al Jazeera with Dominic in a baby Bjorn, which would have been an experience. Unfortunately, somebody else subbed in at the last minute. I'm not quite sure how that would have played out. But of course, no one actually was, at the centre of that was a concern for human safety, but no one was actually harmed during that eruption. But that's not always the case. That was illustrated recently by the Fuego volcano in Guatemala, where pyroclastic flows flowed down the sides of the volcano and destroyed villages and wiped out many hundreds of lives. But this picture is also taken in Iceland. And actually, Iceland takes a considerable amount of its energy from geothermal energy. So this really illustrates that volcanoes can also be natural resources. And in many parts of the world, sort of finding that tension between volcanoes as natural resources and hazards is a really key area of research. And in fact, it's an area of research that we're currently exploring in East Africa as part of the Rift project, where we're trying to find sort of that tension about increasing energy needs, volcanoes as resources, but also as natural hazards. But actually today I really want to talk to you about a third characteristic of volcanoes. So volcanoes can also profoundly impact our environment. And you can see this juicy column of ash and gas blasting off into our atmosphere. And those types of volcanic eruptions all have different impacts on the environment around them. I also love this photo because as a volcanologist, it's sometimes hard to consider how you could possibly make a photo of volcanic eruption more spectacular. But here we have some wonderful lightning going on in the background here. And actually, this is volcanic lightning. This is not a coincidence. This is one of the areas I've also researched in the past. And it's a potential example of it's one of the candidates, in fact, for the origin of life, the molecules for the origin of life, is volcanic lightning on the early Earth. So if we want to understand the impacts of volcanoes on our environments, we have to think about the different types of volcanic activity that we have on our planet. Now, I've organized this as this is basically increasing explosivity, so getting more and more explosive as we go over this side, although that's rather a simplistic way of looking at it in many ways. So many of the volcanoes that you will have seen on the news come in this middle area here. If we look at some of the recent activity, this is a photo from the recent Hawaii eruption that actually happened low down in the East Rift Zone and impacted many of the communities there. People had to be evacuated from their houses. And you can see this sort of someone's house just there, this lava fissure bursting out onto the surface of the planet. So actually this was on the news a lot, but Hawaii is erupting all the time. This was just particularly close to the population. There was also some fire fountaining. This is actually a photo from Etna, but there's some fire fountaining going on as well. But Hawaii, Kilauea, is erupting every day of the year. So some of the volcanism that you don't hear is the kind of everyday volcanism. So we've got some pictures here from Masaya volcano in Nicaragua. You'll see more of this later, but this hot lava lake down the vent here, pumping out gas and aerosol into the atmosphere. And this is a photo here from Volcano volcano. The clue is very much in the name, which is off the coast of Sicily in Italy. And here you have fissures or fumaroles pumping out gas out into the atmosphere. As we go up to more explosive, this is Fuego. This is the recent volcano in Guatemala. Here we have a pyroclastic flow, a hot cloud of ash and gas descending down the side of the volcano, and unfortunately with fatal consequences in this event. And here we have the 1980 eruption of the Mount St. Helens volcano in North America that scattered ash over a large area of North America and punched a great column up into the upper atmosphere. But in terms of our planet, we haven't actually experienced all scales of volcanism in the human era, certainly in the historic era here. So two different types here that we've never actually experienced and documented directly ourselves. This is a so-called supervolcano. We call them magnitude 8 in the trade, but for some reason the press prefer supervolcano. So this is the Toba volcano in Indonesia. So it's about 100 kilometers. This is a nested caldera system, so a series of different craters. And about 75,000 years ago, this had the most enormous, absolutely enormous eruption, probably lasted about a week or two, and enormous clouds of ash would have impacted our planet. So this was about 75,000 years ago. Actually, the most recent supervolcanic eruption was a little bit more recent than that, but still only about 25,000 years ago. But then later on in the talk, I'm going to talk about other type of very large-scale volcanism. And actually, this isn't necessarily akin to this type of volcano like this. It might be more akin to like that. But these so-called large igneous provinces, this is a picture from the Columbia River flood basalts in North America in Washington State. These so-called large igneous provinces go on for very, very long periods of time. So there are periods in the Earth's history when we've had this very heightened volcanism, and we have not experienced. This is the most recent one here that's about 17 million years ago. So there's scales of volcanism on our planet that we just haven't experienced. But let's think first of all about what we can learn from volcanoes that we have experienced. So the first thing we can do is understand what we have going out into the atmosphere from a volcanic plume. So this is magma. It doesn't really exist as a lovely spherical blob in the Earth's crust. But magma deep down, the gases are under pressure and they're dissolved inside that magma. And they're very much like if you open a can of Coke or open a bottle, especially if someone's sort of shaken it up for you, these gases come up out of solution as the pressure decreases on them. And first of all, you get bubbles in the magma like this. And then depending on the material properties of the magma and how much gas you have, you might get a non-explosive eruption, or you might get an explosive eruption like this one here on Mount Etna. And that's actually, I think, one of Mike Burton's photos, and that's Patrick Allard there for scale. So we've got this cloud of gas coming out into the atmosphere here. So ash particles, that's the stuff that we thought about with Eyjafjallajökull eruption in 2010, these little fine rock fragments getting blown away by the wind. But these can also collapse down the sides of the volcanoes in those pyroclastic flows. But these actually settle out of the volcanic cloud relatively close to the volcanic vent. So they don't tend to stay in the atmosphere very long. So it's actually the gas species that we often have to worry about in terms of the environmental impacts. So let's think about what gases we have in a volcanic plume. We have a lot of water in a volcanic plume. That's not a surprise. Water is very ubiquitous on our planet. We have oceans of it. But there's a lot of it in volcanic plumes. But that comes out. But we also have a lot of water already in our atmosphere. So that doesn't make a huge impact on the environment. We also have a lot of carbon dioxide and other minor carbon species in volcanic plumes. And again, in terms of individual eruptions, we have so much carbon dioxide in the environment already that, that it doesn't make an enormous impact, although with the large igneous provinces, potentially it does. But there are other species, there are other chemical gases that are less prevalent in our atmosphere. So, for example, the sulfur gases, sulfur dioxide, a nasty acidic gas. It smells of burnt matches. Hydrogen sulfide here, which is your classic bad egg smell. I got a bit over-enthusiastic once doing a BBC World Service interview about volcanic gases and their different smells. And the guy listened and nodded. And he said, at the end of it, he went, "So would you call yourself a connoisseur of volcanic gases?" Not quite sure that's what I aspire to, but perhaps. What I certainly wish I could do is calibrate my nose, so I didn't have to carry lots of equipment up the volcano and could just take a quick sniff and go, yes, I think a H2S to SO2 ratio of about 1 there. But anyway, so a connoisseur of volcanic gases, these different smells, burnt matches, and hydrogen sulfide. And actually, these sulfur species, as I'll describe in a bit, this sulfur dioxide, can chemically react in the atmosphere. It can oxidize. And when it oxidized, it can form this aerosol, this fine haze of particles of sulfuric acid, which is part of what gives the volcanoes their cloudy appearance. We also have other nasties, like the hydrogen halides, hydrogen chloride, hydrogen bromide, hydrogen fluoride, acidic species that go out into the environment and can have potential impacts. We also, as I'll come on and talk about in a minute, we have the heavy metals like mercury, other metals as well. And the sort of balance between these different species can vary for different reasons. So this is, again, one of Clive's photos, I think from the 2001 eruption of Etna. What I really like about this photo here is that you can see 3 different eruption clouds coming out of the volcano simultaneously, each with a different balance between ash and gas and aerosol in them. So we have these different balances, and each of them have their different consequences. So if we think, first of all, about the impacts of large, explosive Plinian eruptions. So I showed you a photo of Mount St. Helens. This is another of my favorite volcano photos. This is actually an eruption from 2009, Sarachev Peak in the Kuril Islands, just north of Japan. And it's taken from the International Space Station. So the astronauts are kind of peering out of the window with a camera, as I imagine, maybe a mobile phone, I don't know. But no, I think they have proper sort of equipment to take this incredible photo. And what you can see here is the Plinian eruption column, named after Pliny the Younger, who described the eruption of Pompeii that destroyed Vesuvius. No, Vesuvius that destroyed Pompeii. And you can see this column punching up into our atmosphere. You can see it's punched up some of the lower atmosphere. You've got a cap cloud forming on the top there where it's cooled down. And we've got pyroclastic flows going down the sides here. So actually, we've made enormous progress in understanding the impacts of this type of volcanism over recent years. And in part, that's been due to the 1991 Pinatubo eruption. So Pinatubo is in the Philippines, and in June of 1991, it had the largest eruption during the satellite era. So the largest eruption, it's about a 1 in 100-year event. This is actually a picture in the run-up to the main eruption. There was a typhoon coming over during the main eruption, so there aren't such good shots. But you can see this amazing column. You can see a bit of a cap cloud going on there, punching up into the upper atmosphere, punching up into the stratosphere where the all-important ozone is. So in terms of scale of the eruption, the column height went up to about 35 kilometers. And the amount of magma that came out was about 5 cubic kilometers. So that's quite hard to get your head around. So roughly a cubic kilometer is if we took the whole of Greater London and covered it in a metre of rock. So just imagine. A metre of rock over the whole of Greater London is about a cubic kilometre. So you could do that 5 times over. So this punched up a bunch of gas and aerosol into the stratosphere. And as I say, the ash itself settled out relatively quickly compared to the gas. So then we had an enormous amount of sulfur dioxide up there in the stratosphere that slowly oxidized, slowly changed into this haze, this sulfate aerosol haze. And using satellites, we were able to track the progress of that haze. So this is a satellite image of the stratosphere, and these dark colors mean it's quite clean. So you've got a clean atmosphere before the eruption, and then the eruption happens, and the injection point is about here. And you can see the aerosol cloud is spread out around the belly of the planet like this. And then if we roll time forward a bit further, we're now going, this was June to July, we're now going August, September, you can see that that aerosol is now spreading north-south and south-north to the high latitudes, so it covers the whole stratosphere of the planet. And it sticks around. This is now 1994, so this is 3 years after the eruption, and we still haven't returned to these baseline levels like this. And in fact, we can even get visual on this. So these are space shuttle images. So this is the clean atmosphere here. This is the space out there and the surface of the planet down like that. And then after the eruption, we can actually see this layer of aerosol down like this. Now, if we think about it, you know that aerosol in the atmosphere, mist in the atmosphere, changes the way that light behaves. On a misty day, if we've got a low cloud, we know that we can't see as far. So that's because those very, very small particles are basically interacting with the light as it comes in. And what this having this sort of cloud up in the stratosphere like that, what that did was to actually bounce some of the sun's light back off into space. So the consequence of the Pinatubo eruption was to bounce some of the radiation back into space and actually to make our lower atmosphere, the troposphere where we live, cooler. So this is the summer after the Pinatubo eruption, and you can see these blue colours show where things are cooler on average. And the world was significantly cooled for several years after the Pinatubo eruption. So that was one of the largest eruptions that we've been able to study. But actually, volcanoes affect things on other scales as well. I just wanted to play you a little video. This is taken by Emma Liu, who's in the audience in early 2017. And this is back at Masaya's lava lake in Nicaragua, and just shows you how things can behave in a non-explosive fashion. So what you can see here is staring down into the vent. We're about 150 meters away from the lava, if anyone was worried about our safety. We're staring down into this, and you can see, it's mainly the wind you can hear, but you can see bubbles bursting on the surface. You can see gas escaping from the lava surface. You can also see it's very liquid. It almost looks like a kind of just the sea sort of sloshing around. It's very mesmerizing, actually. I could have quite happily sat there for hours just watching it go. Actually, I went there in late 2017. I was there last December. And I arrived a couple of days later. My colleagues decided to play a trick on me because I'd been very, very excited about seeing this lava lake. So they pretended that the lava lake had gone away. It's quite embarrassing how long it took me to work out this was a trick. There was a massive queue of people trying to get up to the volcano for nighttime, and I was still going, oh, there's a lot of people want to go up in the darkness. We got to the top, and there was a sort of orange glow, and I said, it's a lot of crater glow when the lake's gone away. And then finally the penny dropped. So after all my career in volcanology, I still don't seem to have worked out that volcanoes glow and are hot, which is somewhat disappointing. So the lava lake's very, 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 very spectacular, but it pumps out a huge cloud of gas and aerosol into the atmosphere. So this is actually the best view of the volcano cloud is early morning from Managua Airport. So this is looking south from Managua Airport. There's Masaya. That's where the lava lake is there. And you can see this cloud of gas and aerosol making its way, being blown downwind towards the Pacific Ocean, which is basically over there. So this was actually taken early morning on my birthday last year. So I was feeling a little bit grumpy about spending most of my birthday in Miami Airport, but at least this view made up for it in some ways. But you can see as well that Masaya doesn't have much elevation, so actually the downwind communities get fumigated by this volcanic gas. And the closest of these downwind communities is El Panama, which is just about here. So it's only 2 kilometers from the active vent. And if you go there, and we've been working with the local community there, they really feel the presence of the volcano on a daily basis. So you can see that this is the sort of typical sort of vegetation there. And it's basically a sort of reduced to tropical cloud forest to yellow scrubland. This is a picture of one of the houses. It's a very poor community in any case. They have many problems, including lack of running water. But they're not actually able to use nails to keep the roofs on their houses. They have to tie it down with ropes. The nails rust too quickly. All their pots and pans rust as well. And many of them have breathing difficulties. And of course, this has had economic problems for them. So the volcano switched back on in about 1993. And since then, they've had to change the sort of agriculture that they do. So they used to grow coffee, but you can see the volcano burns the leaves of the coffee plants. It's very sensitive to that. And so they've had to adapt, and they've actually found that pineapples and dragon fruit grow very well in this acidic environment. We actually made a video about their lives, so you can look that up on YouTube. We went and took a massive screen and showed the village this video that we'd made. And we showed them some of the lava lake footage, like the stuff I just showed you. And what I found particularly moving is that these people only live a couple of kilometers away from that active vent, and the volcano impacts on them every single day of their lives. But very, very few of them had actually been into the national park because of the cost of going into the national park and seen that volcano. So they were sort of looking into the mouth of the beast for the first time. So this is some of the ways that volcanoes can impact our environment on the present day. But as I said, the Earth's past holds episodes of really, really much larger scale volcanism, or very different types of volcanism. And it's interesting to think what we can learn about these impacts that they might have. I remember early on when I was doing my PhD, I went to a lecture and I was sort of transferring from chemistry to earth sciences, so I was trying to get my head around this new subject area. And I went to a lecture, I don't remember who it was by, but they said, they were talking about the geological timescale and the age of our planet. So they said, if you hold your arm out like that, and if this is 4.5 billion years ago, that's when the planet was formed, and your fingertip is present day, how long do you think humankind has been on the surface of the planet? And we all made guesses, and I thought we might get a few knuckles in there. But actually, if you just take a nail file and draw it once across your fingernail there, that's how long human beings have been on the surface of the planet. So it's really, it makes me feel a bit vertigo, actually, just thinking about geological time and how long. But on geological timescales, we have these very, very large events. So this is, as I said, the Columbia River flood basalts. That's the most recent, about 17 million years ago. This is another example. So this is India, here, the subcontinent. And these are the Deccan traps. That's what they look like in the field, these enormous piles of lava that build up over about 1 million years in Earth's history and cover these enormous footprints on the surface of the planet. So if you remember that about a cubic kilometre was about 1 metre over Greater London, these things put out about 500,000 to 1 million cubic kilometres. So that's 1 million metres over the surface of Greater London. So it's enormous volumes of magma that come out into the surface. And of course, they come out over 1 million years. So they're not all coming out at once. And thinking about how they come out is a very interesting question, how explosive they are, how high their eruption columns get, and how quickly the eruptions go on. And the surface of our planet is absolutely peppered with these deposits. So this is the Deccan here that we were just talking about. We've got the Columbia River flood basalts over here. But just to kind of draw your eye to a couple of others, here we have the enormous area of the Siberian traps. And if you ever are fortunate enough to take a daytime flight from London to Tokyo and you get a window seat, just open the window and look. You sort of fly for hundreds and hundreds of kilometers over these stacks of lava. It's absolutely awe-inspiring. And that's the Siberian traps that were erupted there. And some of them have actually been torn apart by plate tectonics. So the slightly strange abbreviation here, CAMP, stands for the Central Atlantic Magmatic Province. And you see that that's been torn apart, North America, South America, and Africa there. And that's because the continent Pangaea was torn apart at about this time. And I'll show you a sort of reconstruction of that in a minute. So in order to understand these, we do go to modern-day analogues. This is a picture from the Hollerun eruption, relatively recent, in Iceland. That was a sort of analogue in terms of these fissure-type eruptions that we have. This was about a cubic kilometre of magma again. It came out over about 6 months. And this is a very spectacular photo, and again answers the question of how can you make a volcanic eruption more spectacular? You just stick the northern lights in the background. I still haven't seen the Northern Lights. I very much hope to see a volcanic eruption with the Northern Lights one day. I think that's not too much to ask, please. And we do experiments. So this was work led by Anja Schmidt in Cambridge and Evgenia Ilinskaya in Leeds. We basically studied the impacts of this on the air quality in Reykjavik, in nearby towns, but also more broadly in terms of Northern Europe as well. Actually, these types of fissure eruptions are now on the UK National Risk Register in terms of their potential impacts. But if we go back and look into the geological record, we can actually look back at how the planet's environment has evolved. And perhaps one of the most stark ways of thinking about environmental change is thinking about biology and thinking about the massive overturns that we see in biology during some periods of Earth history. So this is part of the geological timescale here. It only goes back to 600 million years, so all really relatively recent, really. But and what I picked out here, we've got basically this is showing you how many species there are on the planet. So what you can see is these jump downs, and these are what we call the mass extinction events. So the one that you probably all heard of is the end Cretaceous mass extinction event. This was when the dinosaurs died out. I've got some pictures here that one of my paleontology colleagues gave me of a dead dinosaur. The dinosaur here, having eaten another dinosaur, is now about to die. Of course, I already showed you this coincides with the Deccan traps. It also coincides with evidence of an asteroid hitting the planet, so somewhere near Mexico. We've got a little cartoon here. There are lots of these sorts of cartoons on the internet. The internet is a wonderful place. And this is one dinosaur saying to the other, hey, check it out, a shooting star. That's a sure sign of good luck, my friend. It turned out not to be such a good sign for the dinosaurs, as is famous. So you've got the Deccan traps and the Chicxulub impact hitting the planet at the same time. The planet doesn't react well, and the dinosaurs suffer. But if we go back to these other mass extinctions, in fact, the end Cretaceous isn't even the largest mass extinction event, not that anyone's counting, but the end Permian here is the largest of those. And while you can argue about what caused the end Cretaceous mass extinction, one thing we can see is that actually these big five, 4 out of these big 5 mass extinction events coincide with large igneous provinces. So the end Triassic here is the Central Atlantic. Then the Siberian traps that I already pointed out to you is the end Permian. So people have sort of pointed the finger at these large igneous provinces actually at causing this massive overturn here. So if we home in a bit on this end Triassic mass extinction here, because I'm going to sort of talk about some of the work that we've been doing on that. This was the extinction before the end Cretaceous here. In fact, we published a paper on this, and I ended up on Radio 5 Live doing an interview about this end Triassic mass extinction event. I wanted to talk about the volcanoes, and Adrian Charles very much wanted to talk about T-Rex. So the problem was the work we'd done was about volcanoes in the end Triassic, and actually T-Rex didn't come along for over 100 million years later. So the conversation went a little bit like, well, I want to talk about volcanoes in the end Triassic, and Adrian Charles going, what about T-Rex though? And me going, well, T-Rex didn't come along for a lot longer, but in a way, the end Triassic mass extinction cleared the way for T-Rex. Okay, good. So it wasn't exactly the message I was trying to get across, but we sort of met midway somewhere in the late Jurassic, I suppose. But at this time, we basically get massive overturn. About 76% of all species are lost. They're poster child sometimes of these sort of crocodile-like species that didn't make it through. And it's tied together. We've got Pangaea here, where all the continents are sort of clustered together. And this is the extent of the Central Atlantic magmatic province that is the kind of one of the potential smoking guns for the volcanic eruption, for the mass extinction. But we've got some real challenges. We're going back a very, very long way in time. This is over 200 million years ago. Kind of the mind boggles when you think about it. And the way that we record the change in the environment, so these mass extinction events, is by looking at sedimentary rocks. So this is just to sort of show you what might happen. Here we have a lovely thriving ecosystem then something happens and we get an extinction. So we've got the deposits from a thriving ecosystem, and then biology kind of disappears, or some species disappear in any case. And then we have a recovery period, and then we go back to a slightly different thriving ecosystem. And this is recorded in the rock record. So we go from a pre-extinction, lots and lots of different fossils, to few fossils, to a few more fossils, and then a full ecosystem again. So those are kind of, that's the way that it's recorded in the sedimentary rocks, and we're defining that mass extinction often by the last occurrence of a particular species. And you actually don't have to go very far to walk through a mass extinction. If you go down to Lyme Regis, just on the south coast of the UK, we take our second years there, you can walk through a mass extinction. You go down to Lyme and you turn right, and the mass extinction is just on your right by the traffic lights. Not quite, you have to go on the beach, but it's a beautiful walk. You turn right and go around a couple of bays, and then you can basically walk up through these Triassic rocks here, through the mass extinction event to the ecosystem recovery. Because of the way that the rocks lie, you can actually walk through them on the beach. You don't have to do any scrambling up and down cliffs. And this is one of the famous ammonite pavements, which are from the recovery phase. Those are my beautiful geology shoes for scale there. So sometimes we can just go and sample through the rock stratigraphy like that to find where the mass extinction is. Sometimes we have to drill cores. This is an example of a core covering roughly the same period from North America here. So we've got these cores like this. These are the sedimentary rocks here, and they record the mass extinction. But one of the challenges is then to tie that together with the volcanic record. Now, the end Triassic is actually really special because sometimes we have these lavas in the same columns as the mass extinction, in the same sedimentary columns. So this is an example here. This is the North Mountain basalt. It's there, number one. It's in Canada now in the Fundy Basin. And you can see these are the sediments that record the biological record, and then you can't really miss it. There's a massive lava flow. You can see some nice cooling columns in this one here. There's some people there just to give you a sense of scale. So the end Triassic, we do have some tie points like that. But even so, that's just one flow going on in this province here. And what we really like to know is what's the whole Central Atlantic magmatic province doing at any one time, and how is that impacting the biology? And one of the really challenging things is dating these rocks. So this is just to show you, these are a series of different flows all numbered around here. And these are the dates taken from single zircon crystals. So we're using radioactive decay as a clock here, and these different dates here, and you can see the enormous range of values that you get. And so what we're trying to do is to take this timescale with these error bars up here of the volcanism and tie it together with the biology and what's going on in the sedimentary column. And that's really, really tricky. So actually what we'd really like is a fingerprint of the gases coming out of the volcano in the sedimentary column. And what I'm going to try and persuade you in the last part of the lecture here is that we can learn something about that from sitting in volcanic vents. This is me at the top of Etna. This is Voragine crater. It's all changed up there now. Volcanoes do that. My mum will be very pleased to see I'm wearing my sun hat underneath my helmet. So I'm really belt and braces on that UV protection, which setting a very good example. And the elements I'm going to talk about to give you this example of this is actually the element mercury. So mercury is a toxic metal. It bioaccumulates in the food chain. This is a tuna fish eating a smaller fish here. And those of you who've been pregnant or been following other people being pregnant, you know that pregnant women are told not to eat too much, I'm already in the drinks reception, eat too much tuna because of the mercury that bioaccumulates up the food chain. Now, mercury is a really, really fascinating element. If you're a chemist like me, it has an absolutely unique electronic configuration. But to the rest of you, it might be more well known as the only liquid metal. So this is actually a Brazilian artisanal gold miner pouring some mercury from his hands into a pot. So those of you who are old enough might remember the excitement of a thermometer breaking in the physics lab, and those little silver blobs of mercury running around, and the mercury clean-out kit having to come out. It's a high point of school science. And it's in the background air all around us. If you take a deep breath now, you've just breathed in about 1 to 2 nanograms per cubic meter of mercury. And that's not going to do you any harm, but if it was in much higher concentrations or as methyl mercury, it really would. Volcanoes are a major natural source of mercury. Because it's such a strange metal, it not only is liquid at room temperature, but it also, quite a lot of it can be gaseous as well. So it can actually get a very, very long way in the atmosphere and travel with gases like sulfur dioxide and carbon dioxide. I've been working on mercury for a very long time. It all started in 2002 when I had a random conversation with another student on a research course who asked me how much mercury came out of volcanoes. And I didn't know, but I've been working on it ever since, which might suggest I'm a bit of a slow learner, but actually there's turned out to be lots and lots of different things to study. So I thought I'd just run you through a little bit about how the field sampling goes on volcanoes. So I'm going to talk you through a field campaign here, which was on Mount Etna in Sicily, and we were staying in a town called Nicolosi, down here on the sides of the volcano. And this was actually the view from where we were staying. So you can see the smoking, fuming volcano up there, lovely. And every morning we get up and eat breakfast, drive up to the volcano. So you drive up, here's the sort of Refugio Sapienza, and then you drive your way up the flank here in 4x4 vehicles. Being Italy, you pick up some really nice food on the way to take up the volcano. And then here we are loading up our backpacks. This is Sandra Ioppa from the University of Palermo. And you can see that we're setting off, trekking in a line here up into this volcanic cloud. So you're having to trek in your gas mask, which is really not all that pleasant. You might be carrying a car battery on your back. You might even have some delicate glassware, which is really very inconvenient. And you're carrying up here. This is a picture of us getting up. I'm looking very casual with the hands in the pockets look, wearing our gas mask. This is Andrew McGonigal, who is in the audience tonight, carrying his vanity case. He can't go anywhere without it. Really didn't need it at the top of the volcano, Andrew. And no, actually, of course, I'm joking. It's a very complex piece of equipment for measuring radioactive nuclides. Thanks, glad you asked. Coming out of the volcano. Here I am, looking a bit unsteady on my feet. This is one of the guides here on the edge, I think, of the Volcanova crater here, trekking to the measurement site, which might be in this sort of gas cloud here. And this is the sort of equipment we use. So this is actually the equipment we use for mercury. So we've got a series of different types of equipment here. But what we're basically doing with each of them is pumping gas through different collection methods. So we've got filter packs here. We've got little gold beads that we use to collect gaseous mercury there. And we've got the denuders, which are really poorly adapted for doing volcanic fieldwork. This is very delicate glassware. I really can't think of anything worse to do on the side of a volcano than try and put up some delicate glassware. And we've broken many, which is very frustrating, particularly after the measurement and the fact they don't get any lighter when they're broken. You can see everything's relatively low tech, and duct tape is a very important part of our fieldwork. So we just got sort of various different types of pumps here. And actually, low tech is really good on a volcano. So one of my colleagues from France actually has a hoover that he's adapted for volcanic sampling. He calls it his dust buster. He's adapted this for volcanic sampling. And it's slightly weird when you're sitting at the top of a volcano. It sounds like someone's doing the hoovering. A little bit disconcerting. Sometimes we take slightly more sophisticated electronics up there as well. So these are real-time measurements. So this is giving us sulfur dioxide gas. This is mercury gas, for example. So with these types of equipment here, we take the stuff down the volcano and then analyze what we got in the lab, and we're able to tell things about what's coming out. Sometimes it's very nice at the top of Mount Etna. You can see Andrew and Sandra here having a nice little sleep in their gas mask while the equipment runs. You can see Ken Sims and me here. We're obviously feeling very, very optimistic, so we're trying to change filter papers at the top of the volcano. We've got tweezers, and Ken's even put on some clean lab gloves at the top of the volcano. So we're obviously feeling very optimistic that we can manage this. So conditions are quite benign. But then rapidly the weather can come in. So this often happens at the top of Etna. This is Andrew checking his vanity case. This is a horrible acid cloud that basically kind of clings to your skin and clothes. People's glasses can get etched. And it really, really isn't very pleasant. And it can be very cold and wet as well. And I dug out this photo, which I think is one of Clive's from one of my first field campaigns to Stromboli during my PhD, where I went up to the top and then realised I forgot my windproof. So there's a lot about improvisation when you're doing field campaigns. So not to have to go down from the volcano, I've just wrapped myself up in a bin bag in order to stay sampling. That's just the level of dedication that I had as a PhD student. But actually making these measurements allowed us to really contribute to science and policy making in quite an unexpected way. So back in 2013, the UN Environment Programme negotiated something called the Minamata Convention on reducing mercury emissions. And a really important component of that was understanding the background mercury cycle, of which volcanoes are a really important component. And so we were able to write these briefing notes with DEFRA in order to actually inform that process and to think about how they keep track of how successful the convention has been. But it also turned out that it was really told us something about things that went on hundreds of millions of years ago. So if we go back to the Central Atlantic magmatic province 200 million years ago, and we think about its relationship with the end Triassic extinction, what we were able to do is actually start looking for mercury in the sediments as a fingerprint of the volcanic eruptions of the large igneous province. So I'm just going to sort of show you one result here. So here we have some columns. They're labelled in this diagram here with the different letters. So we've got one from St Audrey's Bay in Somerset, which we tried to visit last time we were going on holiday, but unfortunately the weather came in and no one wanted to get wet and cold. And then this is an Austrian core here, and then one in Argentina. And what we can see is here we have the mass extinction recorded in the sediments here. And we see we've scaled them all the same, so the peaks are a little bit different in different places. But we see this kick up in mercury in all these places. So what we're seeing is very large-scale emission of volcanic gas into the environment. And actually, because of the particular interspersing of the lava flows at the end Triassic, we know that this flow here in Morocco was going on. This large episode of large igneous province volcanism was going on at the same time. So we can almost feel as if we can put our finger on that little puff of mercury coming out in our lab back in Oxford. It's almost like you can see this is the kind of whisper, the fingerprint, if you like, of that lava flow that was erupted over 200 million years ago. And for me, that was sort of quite an exciting moment to see that. This is a busy slide, but just to kind of give you a flavour of what we're trying to push to do now. Now we have something that can fingerprint when the volcanic emissions were going on from the large igneous provinces. What we can try and do is tie that together with other information from the sedimentary record. So we can tie together this puff of mercury from the large igneous province with other indicators of things like carbon dioxide in the atmosphere. And we can really try to take these events apart and really understand how the environment was changing, how the atmosphere was changing, and how biology was changing in hand by that. And another thing that we can start to do is some of you will have not missed the fact that of these 5 mass extinctions, we've got these 4 large igneous provinces, but there's one here, the Endor division, that doesn't have a large igneous province associated with it. Now that could be because it's so old. The rocks might have been destroyed. They could have been subducted, taken back into the center of the planet. Or it could be that there's a different trigger. But if we go and look for the mercury spikes in these rocks in this large extinction event, then perhaps we can sniff out that lost volcanism and that lost trigger, or test the fact that maybe it was a different thing that triggered that large extinction, that mass extinction event. So I really hope that I've convinced you that there is lots to learn by standing this close to a lava flow. This was actually a photo from 2006. I'd set out from leafy Oxford at 6 a.m. and by 6 p.m. I was standing by a lava flow on Mount Etna, and I can confirm that it is very hot and it does glow. But I hope that I've been able to convince you that there's things that we can learn that are really, really relevant to our planet today. Well, I've given away all my slides now, that are really, really relevant to our planet today, but also can tell us about things that have happened hundreds of millions of years ago and how our planet came to be how it is today. So I just wanted to finish off, because this is, as well as being a great honour, it's also a chance for me to say a few thank yous, which I don't always get to say. And obviously, science is a fundamentally collaborative enterprise. And so receiving an award like this is truly only made possible by the vast array of talented people that I've been fortunate enough to work with over my career. So I fear to thank them all individually would risk extending this lecture by another hour. So I've made this photo montage to record my thanks. But I just wanted to pick out a few groups and individuals. So I wanted to thank Clive, David, and Andrew for being fantastic, inspiring, and fun people to work with during my PhD. I've got a bit of a flavour of some of that. And of course, since. I want to mention all the research students. I'm delighted to see some of them in the audience today, postdocs and research fellows, who I've had the privilege to supervise and collaborate with. The comic group, particularly Tim, Fran already mentioned that. The Streva project, particularly Jenny. The Rift Vault project, especially Juliet, Kathy, Marie, and Kathy. Lots of Kathys in that. The Unrest project, particularly Evgenia, and the Deep Volatiles program, especially Chris. I also wanted to really mention the incredible organisations and individuals that I've worked with and learned so much from in volcanically affected countries. So from INGV in Italy, so especially Sandro, Addis Ababa University in Ethiopia, especially Gezahein, Inater in Nicaragua, especially Wilfried, and our thoughts are very much with them in the current difficult political situation. The USGS in Hawaii, particularly Tamar and Jeff, and Sergey Amin in Chile, especially Alvaro and Jose. And that's just to name a few. I also want to extend heartfelt thanks to all my colleagues and friends within my scientific collaborators, but also my department in Oxford, the wider university, and of course beyond, and disconnected from academia, who have offered me constant advice and support and distraction, and sometimes a shoulder to cry on too. I'm not going to get emotional, but the last 4 years in particular have been incredibly tough for us as a family, and I'd really not be standing here today without all of you. And on that note, I really must also mention the incredible work of Cameron's ward at the John Radcliffe Hospital in Oxford. And last, of course, to my family, to my parents and sister, for their constant love and support and encouragement throughout my lifetime. And to David, Alice, and Dominic, I hope you spotted the emoji in the slides, guys. The world is wide and ancient, full of wonders, and some of which I hope I've shared tonight, but you're at its centre for me. Thank you very much.
Thank you very much for the most amazing lecture. It was truly fantastic because it wasn't just informative, it was also enormously entertaining. And I'm sure that everybody in the audience has got, I'm sorry, I have to say, there's some very burning questions. Yeah. And so we're going. What you did there. so I think we'll just spend the next 5 or 10 minutes or so, if people have questions. Could you raise your hand and somebody will bring you a microphone, and please wait until you've got the microphone in your hand before you say anything. So there's one here.
Hi, I'm probably in danger of just throwing random scientific words together, but is there any connection between volcanology and the current climate change that we're really dealing with now, or is it actually the other way around, that you're learning more about volcanology and how it's affecting?
There's a lot of things to say, I suppose, about that. We know that volcanoes, in a relatively subtle way, react to other external forcings in the Earth system. So when we came out of the last glacial maximum, for example, when the glaciers receded, if you go to places like Chile or Iceland, particularly in Iceland, actually, you see a spike in the volcanism rate because of the changes in pressure in the Earth's crust. So there's that aspect as well. Over longer time scales, things like the carbon dioxide coming out of volcanoes can impact in terms of longer term climate. In terms of current climate change, I don't think there's anything really that's going to get us out of it in terms of volcanoes, unless Pinatubo was going off every year. And of course, people have suggested by the analogue to Pinatubo that we should put some man-made aerosols up into the stratosphere. In fact, there was a Royal Society report on this very thing a few years back. I don't, and that's come out of the kind of inspiration of volcanoes, I guess. I don't think it's personally a very good idea myself. You're kind of tampering with the incoming radiation to sort out the problem with the outgoing radiation, and you have the whole hydrological cycle in between. So there's many things that can help us in terms of understanding. We can also test climate models against volcanic forcings like Pinatubo, for example. So there are certainly links, although in some cases they're a little subtle.
I would like to ask a question. So you showed all these massive explosions and eruptions, but they were many years ago. So the question I have is, are we going to have another period of really severe volcanic activity, or is the Earth cooling down? Were they just there in the past and they're no longer going to happen? Or is it likely that they might come back again, and if so, why?
So you think, meaning large igneous provinces?
Yes, yeah,
so
like that.
We think these are driven from relatively deep inside the Earth, so sort of areas of hot material rising up from relatively deep inside the Earth. Perhaps the core mantle boundary, we're not quite sure. But these plumes rising up in the Earth. The Earth is cooling down, so over very long time scales you might see that less. But I think that there's still enough energy in the old girl to probably at some stage in the geological future give us another large igneous province. But remember, the gaps between them are incredibly long.
Yes.
So we don't have any evidence that that's about to hit us, along with Brexit.
So we're safe for a little while. Safe for a little while yet. Any more questions? There's one down here and another one here. If you bring it here. One here.
Sorry. How easy is it to use historic data on volcanoes to predict sort of how often they're going to come? Does it happen like that, or is it completely random?
Sorry, I didn't quite catch that.
Can you use sort of historic volcano eruptions to predict how often they will come in the future, or can you not predict it based on historical?
Yeah, so when we have good historical records, they could be really key in terms of. So if a volcano is showing unrest, one of the first things we do is try to understand what it's done in the past in order to make at least a best guess at what we think will happen in the future. And if we have good historical records, then certainly that's a real gift to draw upon. It's very patchy, so some areas of the world you have excellent historical records. Santorini, for example, we've got a great record of what's been going on. In other areas, we really only have a very recent snapshot.
There's a question here.
Thanks. That was great and so engaging. My question was about you showed us how the atmosphere changes after the volcano and the gases in the atmosphere and how they spread and the temperatures. And your top left-hand picture of the world was normal. I just wonder how you work out what normal is. So how do you establish the baseline?
So time averaging, and you're right, you would sort of look for a relatively volcanically quiet period, and everything's relative. So you are picking, you make your colours dark to show the change. So you're right that you could have some background aerosol in the stratosphere in any case. But I think that I think that that slide is a composite image of several years, it may be even 10 years. So it's kind of taking an average, if you like, which sort of smooths out the variability that you see in something like the stratosphere.
There's another question here, and I think that might be the last one.
I wonder if you could tell us about the connection between earthquakes and volcanic eruptions. I mean, there certainly have been some but is that just chance? Or do you always need to have an association of earthquake and a volcanic activity?
Well, I suppose in the first order sense, they're both tectonic phenomena. So they're associated with, not all volcanoes are, or not all earthquakes are, but they're largely associated with plate boundaries. So they tend to co-locate. So that's sometimes why you sort of have that that connection there, because you have the two plates moving in relation to each other, and that both causes the earthquake and causes the volcanism. We did some work, this is part of Seb Watt's PhD, we did some work looking at the historical records in Chile of volcanic eruptions. And in Chile you get very, very large earthquakes. And it's quite famous because Darwin went there and there was an earthquake, and then some volcanoes went off and he made that link. And so we did some more detailed statistical analysis on that. And you do see some statistically significant association there. But it's not quite as clear as saying the earthquake happened and so the eruption was triggered. You have to have your volcano kind of on a trajectory towards an eruption, and then the earthquake kind of shakes it up a bit and might weaken the crust or might shake that gas like the Coke bottle again. It's all about Coke with me. It should be champagne, shouldn't it? And shakes it up like that, and then you get bubble nucleation, and that can push it on its way. So it's hard to sort of say, oh, that volcano was triggered by that earthquake.
Okay, I think we have to finish because I've been told we have to finish at 7:30. So what I'd like to do now is thank Professor Mather again, and then I'm going to present her with the medal. So. And so, on behalf of the Royal Society, many, many, many congratulations for winning this prestigious Rosalind Franklin Award. And here is the medal itself, and here is the scroll, and there is a cheque on its way, I believe. Well done. That was totally brilliant.